Hi everyone! The goal for today's lecture is to understand how Scala infers the error type of an either. It will demystify the process and give us a strong understanding of the Scala type system. Having said that, this video is quite theoretical, so feel free to skip it and come back to it later if you're interested. Now let's start by studying the Scala type system. In Scala, types have parents. For example, a role is the parent class of reader, editor, and admin. Another way to say this is that reader, editor, and admin are subtypes of role. This subtyping relationship is defined using the extends keyword at the end of a class definition. Subtyping allows us to adapt the type of an object. For instance, when we create the variable Bob, Scala infers its type to be editor, because this is the most precise type. And if later on we need a value of type role, we can reuse Bob. Scala will automatically upcast the type of Bob to role because role is a parent of editor. So it's always safe to upcast, we are just losing precision, but it's not safe to downcast. For example, we can't safely transform a value of type role to reader. Now let's have a look at the place of role within the entire Scala type system. As you can see, role is on the right-hand side of this diagram. It has one direct parent called anyRef. AnyRef is a parent of all references in Scala, meaning all objects that live on the heap, such as string, local date, or standard classes that we create ourselves. As a side note, anyRef is the same as JavaLang object, the top-level class in Java. AnyRef has also an equivalent for primitive. It's called anyval. As you can see, anyval is a parent of both int and boolean. Then at the top of the hierarchy, we have any, the biggest possible type in Scala. Everything extends any. Cool, so now that we know about the parents of role, let's have a look at the types below. There are two specific ones. First, there is null, which has only one value, null in lowercase. Null is a subtype of all references, which explains why we can assign null to a string, but we can't assign null to an int. Null, the type, is a subtype of string, but it is not a subtype of int or any other primitives. Finally, there is nothing, which is probably the weirdest type in Scala. Nothing is a subtype of everything, but there is no value of type nothing. It's impossible to create one. We'll study a use case for nothing a bit later on. For the moment, let's just consider that nothing is here to complete this diagram by providing a sort of mirror to any. Any is a parent of every type, while nothing is a subtype of every type. Great! So the purpose of this video is to understand the type inference of either, which requires understanding the subtyping relationship between eithers with different error types. Now, either is quite complex because it has two type parameters. So I propose that we study option first, and then we'll come back to either later. So the question is, what is the subtyping relationship between an option of role and an option of editor? Basically, there are three possibilities. One, it behaves the same way as role and editor, meaning that an option of editor is a subtype of option of role. Two, it is the other way around. Option of editor is a parent of option of role. Three, both types are unrelated, they are like int and string. I'll let you pause the video and think about it for a minute or two. Option maintains the same subtyping relationship. If we have an option of editor, we can assign it to a variable of type option of role. Now, what about other type constructors? For example, how does it work with list? I'll let you pause the video and think about it. It works in the same way. a list of editors is a valid list of roles. So do you think it always behaves like this? Or is there any type constructors that behaves differently? I'll let you pause the video and try to find a counterexample, if you can. The answer is no. The subtyping relationship is not always maintained. It depends on the type constructor. For example, in Chapter 2, we studied a type constructor called predicate, which is essentially a generic function from A to Boolean. Here I define hasDefaultFont, a predicate of editor which checks if their favorite font is Arial. Now, I claim that if we could upcast hasDefaultFont to predicate of role, then it would be completely broken. Indeed, if this was allowed, then we could use this predicate to evaluate any values of type role. So we could call role predicate.eval with an admin or a reader, which doesn't make sense. hasDefaultFont only knows how to evaluate an editor. It has no clue how to process an admin or a reader. So predicate of editor shouldn't be a subtype of predicate of role. Actually, it should be the other way around. If we can evaluate all roles, then we can evaluate a subset. This means that predicate actually reverses the subtyping relationship. Editor is a subtype of role, but predicate of editor should be a parent of predicate of role. If you find this weird, that's completely normal. I encourage you to go through a couple of examples with a pen and paper. It will eventually make sense. So we have seen that some type constructors maintain the subtyping relationship. We say that they are covariant, while other type constructors reverses the subtyping relationship. In this case, we say that they are contravariant. Now, the million-dollar question is, how does Scala know if a type constructor is covariant or contravariant? By default, Scala assumes that all type constructors are neither. For example, if we create a class foo with a type parameter, then foo of editor, foo of admin, and foo of role are all unrelated. We say that foo is invariant. To make a type constructor covariant, we need to add a plus sign in front of the type parameter. The standard library does this for option, list, and even future. On the other hand, if we want to make a type constructor contravariant, we need to use a minus sign. This means that we should define predicate like this. Finally, we have everything we need to study either. Both type parameters of either are covariant, meaning that they both maintain the normal type hierarchy. Let's take a look at the seal trait syntax because it is more explicit. With this syntax, we can see that both left and right are classes which extend either. What's particularly interesting is that left and right only define one type parameter, and the other one is set to nothing. Let's go through an example to see the subtyping relationship of either. When we type left of something is missing, we get a value of type left of string. Now, because the class left extend either of e nothing, it means that we can upcast this expression to either of string nothing. Finally, because nothing is a subtype of everything, and either is covariant on the second type parameter, we can upcast the second type parameter to anything we want. In this case, we get an either of string int. And the same thing happens with right, except that it is the first parameter of either that it is set to nothing. Okay, so now that we understand how Scala upcasts the type of left and right to the expected either type, now let's have a look at how we can combine eithers using a for comprehension. In the simplest case, we have a for comprehension where all the lines return the same error type. For example, here they all use string. So in this case, the resulting either also uses string. Note that the right type of the either is always the type of the yield expression. Now, if the eithers inside the four comprehensions return different error types, for instance too small and invalid characters, then the resulting either will have an error type of username error, because it is the closest common parent of too small and invalid characters. This closest common parent is also called the least upper bound, or LUB. Let's have a look at a couple of examples. What is the least upper bound of two types which have the same direct parent? As we have just seen, it is the parents class. Next, what is the least upper bound if both types are in completely different parts of the type hierarchy? In this case, it is any, because any is a common parent of all types. Finally, what is the least upper bound when one type is the parent of another type? In this case, the parent is the least upper bound. As you're going to see, this last case is very important to understand FlatMap, the main method behind four comprehensions. A naive implementation of FlatMap would look like this, where the next function returns an either of E2 next. This means that both eithers have different success and failure types. Now, the question is, what will be the return type of FlatMap? To answer this question, we need to check the return type of each branch of the pattern match. The first line returns an either of E nothing, because we return a left of value, and value is the error type of the current either. Then the second line returns an either of E2 next, because this is the return type of the function next. Now we know that either is covariant in both type parameters. This means that on the right side of the return type, we'll have the least upper bound of nothing and next, which is equal to next, since nothing is a subtype of everything. And on the left side, we'll have the least upper bound of E and E2, which is any because E and E2 are free type variables. We don't know anything about them. This is a problem, because if E and E2 are too small and invalid characters, then we would like to infer username error, and not any. Any is not wrong, but it is imprecise. We are losing information. Here, I would like to show you a trick used throughout the Scala standard library to solve this problem. We can add a type constraint to E2, which says that E2 must be a parent of E. It's also called a lower type bound. The benefit of this approach is that we can return a more precise type, because now we know that the least upper bound of E and E2 is E2. However, you might think that we are cheating here, because we don't want to constrain FlatMap to working only with errors that are subtypes of one another. So let's go through two examples to show you that it actually works pretty well. First, let's start by flat mapping eithers with too small and invalid characters error. I added type annotations to show you the types that are inferred. The problem here is that invalid characters is not a parent of too small, which means that the constraint from FlatMap is not respected. However, we have seen that Scala can upcast the type inside an either so that it matches the expected type. This is exactly what's going to happen here. Scala tries to find the first parent of invalid characters so that it is also a parent of too small. In this case, the correct answer is username error. Now, if we flat map a left of int and a left of string, then Scala will upcast the error type to any, because this is a common parent of both int and string. So really, the important part here is that Scala upcasts the type of an expression based on the expected type and its constraints. In summary, today we have studied the type hierarchy of Scala, and we have seen that when we apply a type constructor to a type, it can either maintain, reverse, or kind of ignore the subtyping relationship of its parameter. When it maintains the type hierarchy, we say the type constructor is covariant. In this case, we put a plus sign in front of the type parameter. When it reverses the type hierarchy, we say the type constructor is contravariant. In this case, we put a minus in front of the type parameter. Finally, when we don't annotate the type parameter, by default, we say the type constructor is invariant. Personally, I always struggle to get my head around variance, but I have an example that helps me to remember how it works. Let me share it with you. When we work with JSON or other serialization formats, we generally need the following three traits. 1. A JSON decoder, which takes a JSON and tries to parse it into an A. 2. A JSON encoder, which takes an A and formats it into JSON. And 3. A JSON codec, which combines both the encoder and decoder. JSON decoder is covariant because A is only present in the output type of the methods. JSON decoder only produces A's. JSON encoder is contravariant because A is only present in the input type of the methods. It only consumes A's. Finally, JSON codec is invariant because it both produces and consumes A's. There are more advanced scenarios, but these cases already cover a lot. Finally, we studied either, which is covariant in both type parameters. We saw that this covariance is crucial for informing the compiler about the subtyping relationship between isers, which means that Scala can safely upcast values when necessary. Variance is a complex subject, but it is the key to fantastic type inference in Scala. And this technique is very common in the standard library, as well as in third-party libraries such as FS2 or ZIO. If you have time and motivation, I strongly encourage you to review the exercises from previous chapters and try to add variance annotation where possible. Cool, so I hope you enjoyed this video, and in the next one we'll come back to the exercises with either. See you soon!